Hello everybody. We're going to solve one one example now about the boundary layer equations that we produced using the derivation in the last video. So what we are going to discuss here, or this example, is about chemical vapor deposition of silicon on a silicon wafer, and this is similar to some problems that we solved in the molecular diffusion part, but in this case we have a turbulence or a bit of turbulence in the system. It's still laminar flow, but we have fluid motion, and in this case we have the silane, which is silicon trichlorosilane, SiHCl3. This is 1% by mole. It's a very diluted mixture or silane gas mixture. The balance is hydrogen, which is almost 99% hydrogen, and this mixture is fed into this chamber, which is the chemical vapor deposition reactor, where silicon or the silane is transferred to the surface by convection, and the reaction takes place, and then it reacts with hydrogen to produce silicon according to this balance equation. So each mole of this silane reacts with 1 mole of hydrogen to produce silicon and 3 moles of HCl. This is the balance of the equation, and the product is HCl, which is produced as gas and leaves with the exit gas. And we know some information, as we said, the mole percent of the silane in the feed gas. We know that the velocity is 200 centimeter per second, and we know that the film that we have here is 15 centimeters by 15 centimeters, so it's a square-shaped wafer. It says here that the gas is like whatever the HCl gas is diluted with HCl, and the hydrogen by hydrogen, and the hydrogen gas is considered as the carrier gas. So this is important because we will be trying to get the physical properties of the fluids or the gas phase that we have, and if we have a mixture of hydrogen, silane, and HCl, it's going to be very, very difficult to get the properties of a mixture. So that's why we make it simple for us by assuming that the concentration is not affecting the properties, and the bulk of the gas is still hydrogen. So the properties of the gas phase is the properties of hydrogen. So this is going to make life very, very easy. We know that the temperature and the pressure is 1 atmosphere and 1200 Kelvin, and the flow over the silicon wafer is approximated as flow over a flat plate, and that's why we can use the equations of flow over flat plate. We know the diffusivity of silane in hydrogen, and the molecular weight of silicon, the density of solid silicon. We all know all this information, and we know some information about the reaction on the surface, that it's a first order reaction, so the rate of reaction is represented by this equation, and the value of Ks is 0.83 centimeters per second. So this is these are all the information that we know. And based on this information, we need to obtain or to calculate two things. First, the rate of solid silicon deposition, how much silicon or the rate of this silicon deposition on the wafer, and the rate of silicon thickness increase. How quick does this silicon layer increase with time? So to think about this, let's think about the first part, which is calculating the flux or the rate, the rate of silicon deposition. If you think about the rate of silicon deposition, then you have to think of this based on the assumption or the information that we know, and some assumptions. So one very important assumption is to assume it's a steady state process. So in case of steady state, let's go back here. In the case of steady state, the amount of or the rate of silicon transfer from the bulk of the gas to the surface equals the rate of reaction equals the rate of silicon deposition, because the balance of this equation or the stoichiometry of this equation is 1 goes to 1. So each 1 mole produces 1 mole. So this is the basis of our solution. So we'll say that the molar rate of silicon deposition is the molar rate of silane consumption by reaction equals the molar rate of convection or convective mass transfer. So if I can calculate any one of these two, the rate of silane consumption or the rate of convection, I'm done, and this is all what I need to do. So we'll look at the equations that we have, and we'll see the possibility of using any of them to calculate the molar rate of silicon deposition. So for the first part, it's the molar rate of silicon or silane consumption by reaction. This is the rate of reaction. It's Ks multiplied by Cs. If you see the units of Ks and multiplied by Cs, it's gonna be the units of mole per centimeter square second. So it's per unit area. So if I want the rate, then I have to multiply it by the cross-sectional area. I know Ks and I know S, which is 15 by 15, but I don't know CAS. So this is one like tricky part here. I don't know the concentration at the surface, so I cannot calculate the molar rate of consumption of silane by reaction. So we can look at the other option, which is the convection or convective mass transfer. So it's the flux multiplied by the cross-sectional area, and the flux equals Kc multiplied by Ca infinity minus Cas multiplied by S. I don't know, still I have Cs here, so it's raising the same concern here. Ca infinity is the concentration in the bulk of the gas. I know the mole fraction, so in a way or another I can calculate the concentration at the bulk of the gas. So I can consider this as an information that I can calculate. For Kc, I don't have the mass transfer coefficient, but I can use the flat plate correlation to get the mass transfer correlation. So coefficient, I'm sorry. So I know the velocity, I know L, I know diffusivity, but I don't know the kinematic viscosity or the momentum diffusivity. But this is something I can get from physical properties database or tables. So I can or I have the information that I can use to calculate Sherwood number, and from Sherwood number I can calculate the mass transfer coefficient. So back to the equations, I can calculate Kc, I can calculate Ca infinity, I can calculate S, but still I have Cas here, as the case for the other equation. So neither of them can be used to calculate the rate of deposition or reaction or whatever. But I can use them together. So if I use each one of them separately, I'm not gonna get anything. But if I use these two equations together, I can have CAS as a function of the other parameters, Ks, Kc, S, and Ca infinity, which are parameters that I already know. So this is the plan now, is to put these two equations equal to each other, and from this we can calculate the concentration at the surface. But we have to get ready for this, we have to calculate all the parameters that we know. One of the challenges is to get the physical properties, and here we have the table of the physical properties of hydrogen. We have the parameter here is the temperature. You pick whatever temperature that you want, and then you see the parameter that you're interested in. In our case, we have the temperature of 1200. So this is the temperature that we are operating at. And here you have the density, heat capacity, viscosity, the kinematic viscosity. So this is the parameter that we want. It's important to look at the header because it tells you what parameter is this, and it gives you information about the units. So it's in meters squared per second, and it gives you information about the values. So what we have here is that it tells us that all the values here are multiplied by 10 power 6. So this value originally was 4.938 multiplied by 10 power minus 6. This was multiplied by 10 power minus 6, and the same for all the values here. So instead of having all of them multiplied by 10 power minus 6 for the whole column, you multiply it all by 10 power 6 and put it here to let the user or the reader know that these values are already multiplied by 10 power 6. So if you want to get its actual value, you have to multiply it by 10 power minus 6 to get it back to its original value. So this is 1109.8 multiplied by 10 power minus 6 meters squared per second. So this is the value. I have multiplied by 10 power 4 to put it in centimeters squared per second. So this is the kinematic viscosity. Now I can calculate Sherwood number. Here this is Reynolds number and this is Schmidt number. I didn't calculate them both or each one of them separately, but Schmidt number is going to be around 3.5. Reynolds number is going to be around 300, 400, something like this. So they both will be important for first for one reason regarding the equation. We have this equation as the laminar, or based on the laminar boundary layer analysis. So I have to make sure that this is a laminar flow, and this is something we can confirm from Reynolds number, which is less than 2000, which means that we are operating at laminar conditions. The second part here is regarding the Schmidt number. I said it's going to be around 3.5, and this is important because we mentioned before, or the previous video, something relating the thickness or the relative thicknesses of the hydrodynamic boundary layer and the concentration boundary layer to the Schmidt number. So Schmidt number, if it's larger than 1, then the hydrodynamic boundary layer is thicker than the concentration boundary layer, and this is something we will check later. So from this I can expect that the hydrodynamic boundary layer is thicker than the concentration boundary layer. From Sherwood number I can calculate the mass transfer coefficient. I know the L is 15, the diffusion coefficient is already given, so I can calculate the mass transfer coefficient. One very important thing that we have to keep in mind here is that the units must be consistent. So if I use the velocity in centimeters per second, so then this has to be in centimeter, and this has to be in centimeter square per second. So you have to make sure that the units are homogeneous. This is very tricky thing. Now we will go back to the equation of equating the flux with the reaction flux. So in this case we can rearrange the equation to have the concentration at the surface equals like a combination of the other parameters that I know. And before we proceed, this is kind of useful relation, because in this relation we can see what will be the concentration at the surface if the reaction is very fast. So if the reaction is very fast, it means that Ks is a large number, so this whole concentration will be equal to 0. And this is what we always say, that if you have very fast reaction, then the surface concentration is 0. But in our case it's not, so you have to calculate it. I know Kc, I know Ks, I don't know Ca infinity. I know the mole fraction of A in the gas phase, and from this I can calculate the partial pressure, and from the partial pressure with the assumption of an ideal gas system, or the gas is ideal gas, we can calculate the concentration as P over RT. So this is what I have here. This is P infinity over RT. The P infinity is YA infinity multiplied by total pressure, and from this I can calculate Ca infinity. From this equation I can calculate the concentration at the surface, and now I can calculate the flux using any one of these two equations. It's Ca infinity minus Cas, so I can calculate it to be 7.05 multiplied 10 power minus 8 gram mole per centimeter square second. The rate is the flux multiplied by cross-sectional area, so I multiplied by 225, which is 15 by 15, and this is the rate of mass transfer. So this is regarding the first part of the problem. The second part is concerned with the thickness of the film, and this is like it's very easy, but you have to have a plan in your mind to see how you can do this. The thickness is what I know about the parameter that is directly affecting the thickness is the rate of deposition. If I have high rate of deposition, then the thickness will increase quickly, and vice versa. So the rate of deposition can be molar rate, and I can calculate from it the mass rate, and from the mass rate I can, by the knowledge of the density, I can calculate the volumetric layer rate of deposition. I can know how many centimeter cubes of the silicon is depositing on the surface, and I know already the area. So if I can divide this volume divided by the area, I can get the thickness. So this is how we will proceed. So I put this as I'm going to use the molar flux, because we need the thickness, not the whole volume. So the rate of thickness increase is going to be the flux multiplied by molecular weight to convert it into gram over centimeter square second, and then divide by the density to be in centimeter cube per gram mole centimeter square second, which is going to be centimeter per second, which is the rate of or the thickness increase rate. So by substitution, you have to make sure again that the units are okay, and then you will get the rate of thickness increase is 30.5 microns per hour. So this is the last requirement in this problem. I did one extra thing here, which is the application of the equations that we have been using. So here we have the equation of or the plot of the local mass transfer coefficient as a function of the distance or the plate length. You would see here that at very low values of plate length, the mass transfer coefficient is large, and this makes sense because k is inversely proportional to x power half. X power half, because I have here x power half, here is x, so it's square root of x here. So the k is inversely proportional to square root of x, and this is like a logical thing. Here you see the plot of the concentration boundary layer thickness and the hydrodynamic boundary layer thickness, and as we see, as we know from before, it increases with the distance from the leading edge, and this is what we see. And you see, because Schmidt number is larger than 1, the hydrodynamic boundary layer is thicker than the concentration boundary layer. I like to also do one more thing here, or discuss one more thing here, which is the relation between these two plots. You'd see here that as you go farther or away from the leading edge, the thickness increases, which will impact the mass transfer coefficient, because in this case you have larger distance to travel through. So you see here the thickness where the concentration changes is less than 1 centimeter. Here it's 3.2 or something centimeters. So it's more than 3 times the thickness here, and that's why this long distance will represent more resistance to mass transfer, and then mass transfer coefficient will be less. So this is very logical thing. So this is regarding this problem. We have in this chapter one last part that we will cover. There are more details in the textbook, but I'll just go through this part. I'm not gonna discuss the analogies. It's not gonna add a lot, so I'm not gonna waste time in this. We will see quickly the approach that's used to predict the mass transfer coefficient using the approximate boundary layer analysis, and we'll see the final equation, and we'll wrap up this chapter and to put the main points together to make sure that we get the idea or the main output out of this chapter. So this is all for this video, and I'll see you in the next video, inshallah. Goodbye.